Welcome to this unit on probability theory. I split it up into 10 short stories. Start with a little introduction. Probability theory is a pillar of mathematics. I wrote once a book about it. I learned while writing this book, and I taught that topic for a couple of times, and it's just a beautiful thing. There's gambling, there are processes, there's lots of beautiful mathematics is involved, lots of dynamics, and lots of stories, and we are going to look at some of these stories. Story 1 deals with Martingales. We are going to the casino. We are playing roulette, so the ball is thrown in the clockwise direction, while the wheel is spinning the anti-clockwise direction. And what we are going to do, we are going into the casino with lots and lots of cash. So I'm putting $100 I'm putting $100 on black. So I lost. So I have a minus $1,100. I'm off. I lost $100. I'm going again. Now I'm betting $200. So I'm betting $200. So I'm betting a 2 here on black again. So let me just throw that again. The ball goes clockwise and the wheel goes counterclockwise. So I'm betting $200 now. Black, I won. I get $200 back. So I have actually won $100. So $200 I've paid, I get $400. And so I have $100, and I'm leaving the casino and I'm gone forever. And I go home and I'm happy I've won $100. So there are mathematical theorems, stopping time theorems, Martingale, for example, that's what's included. Here the Martingale theory is a very beautiful theory, Martingale theory. It's a part of stochastic processes. It's due to dupe. And this theory tells you if you kind of stop it, if you have only finite amount of time to play, or you have only finite amount of cash, then you are losing. And it was a strategy which was in the French casino. It was played. Actually, Martingale comes from Arabic. It means kind of constraint. It was a harness type thing for horses, saddling horses. And people thought at that time that luck is not a matter of chance, but luck is a matter of fate. If you lose in a casino, it was not believed to be that you are losing, because of randomness, but you lose because there was a purpose behind it. And so this is kind of a funny time. And so this Martingale strategy was considered foolish, not because of mathematics, but it was considered foolish because it was against that fate. Completely wrong reason it was considered foolish. Actually, without any constraints, it's a foolproof strategy. Okay, the second story is about conditional probability theory. It's a very important topic in actually Martingale theory is all about conditional probability. And I'm not talking about the Monte Carlo problem here, maybe in class. So because it's kitsch, it is so old, it was from 1991, it was popularized by a columnist, Marilyn Vaussavant, and it produced a lot of wind, for example, in the New York Times and so on. I taught about this in '94 when I taught the graduate probability course. The first textbook which really uses it, I think, is a textbook of Isaac on probability theory, The Pleasures of Probability Theory from '95. And a little bit old-fashioned, but something more interesting and older actually is the following problem. I think it's due to Gardner. It's also too easy. You have just 4 possibilities, right? So you have boy, 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 girl, girl, boy, a girl, girl. So you have 4 possibilities, and then you restrict yourself to one of them is a boy, right? So you restrict yourself to this. This is an event which is the conditional, which you take the conditional probability on, and then there are 2 cases, right? There are 2 cases which are good cases and 3 cases which are bad, so the probability is 2/3. So when I taught this since 10 years, this course, and I always, of course, also included this example, when then a student told me the following variant of the problem, which completely perplexed me. And so it has 2 kids, one is a boy, and you just add the following thing, born at night. What is the probability that the second kid is a girl? So so that's I would not have believed it, but the probability is different, and that completely threw me. I mean, this is just something which conditional probability is so unintuitive. Born at night, how should that actually matter? Let me just write you down the possibilities, all the possibilities here. So there are 7. So the probability has dropped. Amazing example. So this third story is about stochastic processes, random walks. It's usually told as the drunken sailor who walks around. And there's a wonderful theorem which says if you have a random walk in 2 dimensions, so 2D random walker will return with probability 1. But if I have a 3 dimension, if I'm in 3 dimensions, if I'm walking either to the left or to the right or up, forward or backwards, or up or down, I can also go up or down. So there are 6 possibilities. And in principle what I can do is I can make a random walk. So I have here a random number generator. So I throw that. If it's 4 means I go backwards 1 step. 6 I mean I going down. So when we do that, we go randomly around, up, down, left, right, or forward or backwards. Okay, so the story is that in 3 dimensions we will return. In 3D, the drone will no more return. The drone will drift off. So it's a big difference between 2 dimensions and 3 dimensions. Okay, this story number 4, it's a wonderful story. Also kitsch, it's because it's very old. It's the story of the Buffon Needle. So we throw a needle randomly of length 1. So this has length 1 and that's also 1 here. And we ask ourselves, what is the probability that it hits a grate? So the probability to hit the grate and it turns out this is just equal to 2 over pi. So now this one has turned off. I've only this camera. That's fine. You don't need the other camera. There's much more to this. So this is this integral geometry allows you to compute curvatures. You can compute the length of a surface, which is kind of weird. And when you look at the length, so you would have to look at all the possible lengths of all the possible connections. So that's something which we usually do not compute, even in calculus not. But it allows you to do that. We can get a surface and then we can cut it with a random plane. We look at the length of this random plane and we just compute the expectation value. So probability theory is like a microscope which allows you to look into things which you usually can only do with technical tools, like sheaf theoretical tools, like differential geometric. Petersburg casino is a wonderful thing. So you pay pay X dollars for each entry, and what you get. Let's play this quickly. So I decide to pay $100. $100. So let's play that. What I get is red. So I lost. So I only got $1 back. So I'm at minus 99. So that's a thing. So $100 seems to be kind of a big fee. How much would you pay? Now, after you have played that a little bit, you will say, okay, maybe $2. You know, maybe $2. And actually, we would have taken $2 here. We would have lost just 4 times 2, $8. We would have won $3. Maybe $3 or so. But the surprise is, whatever entry you have, when you play this casino, you will eventually win. So the entry fee with 100, if I play this long enough here, I win, because I win with probability 1 over 2 to the n, win 2 to the n. So this is the win. And then I sum that up for n equal to 1 to infinity. So the expected value is infinity for that casino, even so our experience shows we would not even, nobody would pay $10 in that casino. And that's a very interesting case. Economists are also interested in this because the mathematics here doesn't really match with the decision. You know, how much to pay. That's very important in probability theory to have a nice setup. And the analog of Euclid for geometry, right? Euclid did the axiomatic setup of geometry, and Kolmogorov did it for probability theory. Before that, it was just a muddy water. And what one has is omega is a kind of a probability space, which is just the experiments, set of experiments. And then what we have is an algebra, a set. So this is a sigma algebra. This is a set of sets, which is close to that operation of taking, it's a Boolean algebra, but only close to the countable unions and countable intersections. And then there's a probability measure. So these are events. So this is the probability space. These are experiments. And this is the probability. So the probability of an event is defined. So this is a probability measure. This is a P is a measure, which means we actually go from this algebra to 0, 1. To every of these events, we assign a probability between 0 and 1. This is a natural probability space. So we have the following setup. So we are doing we are throwing randomly a chord onto a circle, and we look what is the probability that it's larger than this length here. So you can argue the following way. You spin it randomly and then you see where you are. And you look at this like that. So you take here a point, you spin it randomly, and what happens is you look at the probabilities which are good, right? The angles which are good. So these are angles where you are larger. So you have the chord is larger than that inscribed equilateral triangle. So because this is just the probability is equal to 1/3. You see whether you are larger or smaller, and the probability is 1/3 because that in that range you have a positive case. And then when you roll it like that, then we can kind of see from where to where does it really matter. So this length is equal to 1, this is equal to 1/2, this is also equal to 1/2. So that's equal to 1/2, that's equal to 1/2, that's equal to 1/2. In that range here, if you roll it and you are in that range, then it's larger. If you are here, then it's shorter. So you see when you do the experiment like that, you see that it's 1/2 Finally, we can also do it like this. We can just say, okay, let's just put the center randomly and then I'm putting the chord here through. So putting the chord here through. So I ask myself, when is that chord longer? And then you see that it's actually just the radius 1/2. Right, like here, you see that it's actually just 1/2 here. Radius 1/2, that's the good case here. While these are the bad cases. So if my center point would have been here, then it would be shorter. If it's here, it's larger. But you see that the area of this is equal to 1/4. So what shall it be? Shall it be 1/3? Shall it be 1/2? And shall it be 1/4? And that produced heated discussions for anybody who has not seen probability theory or kind of the setup. What actually matters is what is the measure, what is the probability measure. So these are different experiments. If you make the experiment like here, you get 1/3. If I do the experiment like this and I roll it like this, then I get 1/2. And if I'm doing it like that and I'm throwing randomly things, then the probability is equal to 1/4, provided I'm hitting every point with the same probability. The most famous thing is the birthday paradox. And it's usually stated like that. You have a class of 23 students. What is the probability that two have the same birthday? So it's a relatively large process. It's more likely the probability you have 2 students with the same birthday. So what you can do is you can compute the probability that you have no collision, no common birthday, and that's just then 1 is 365 over 365. Now the second student can only have 364, etc. And that's the sort of probability that we have a common birthday. Is 0.54. Like throwing a dice, that's already a pseudo-random number generator. Or if you are shuffling cards, like here, I have here a shuffling machine. So the machine has shuffled this card, like I'm doing like this. I can also do it like that. But randomness is in every process. If you look in hydrodynamics, this Java lamp, and so I want to illustrate this not with cards or this. We'll talk more about this, but with this bingo thing. What actually happens here is I'm deterministically throwing around these balls. And here the chaos comes in from all these collisions. So one of the possibilities to get pseudo-random numbers is look at the numbers of pi. For example, if you look at pi, so it appears that these digits are random. So they satisfy they pass all the statistical tests which we have. So the number 1 appears with the same frequency statistically than any other number. Any pattern which you have appears with the same probability. So it looks like a random or the square root of 2. So you have also there, when we look at it, but nobody has proven this, that this is really, the case. It's important that we have good pseudo-random number generators. And one of the methods to factor integers, we cannot just search through this. And we'll talk about this in the crypto lecture. So entropy is one of the probably most important notions which we know in science overall. The entropy principle is very important also in probability theory, because when we have a distribution, so f of x is a distribution function, probability distribution function, then on the real axis, what function maximizes the entropy? So the entropy is the integral from -infinity to infinity, and then you have minus, and then fx log of fx dx. So that's the entropy, and in the discrete case, it's the sum. Shannon and also Boltzmann has done that in statistical mechanics, and Shannon in information theory. And so it's a very interesting thing. So you ask yourself, which probability distribution of variance 1 and has the maximal entropy. So it turns out that in the it's e to the minus x square half. This is actually the central limit theorem also, and the Galton board, or bean board. When you look at that and you let the beans flow randomly here, what did Einstein say? God does not play dice. So he didn't believe so much into quantum mechanics, but it's a beautiful theory and it is very successful, and probability theory plays an important role. For example, if we take a set A and then this is the wave, so this is the probability of the particle to be in A. So there are all kind of generalizations of what we have in probability theory. For example, the trace of A always is index. That's a representation of a operator. And we have functions of association index actually has values. Ej and the sum of Ej is equal to 0, Ej is equal to 1. So also in the quantum world, probability theory is very important. It actually is the theory of probability theory. And this is there's a beautiful paradox of Schrödinger cat. So let's finish just with instead of the Schrödinger cat, I'm talking about the Schrödinger bear, because that I don't have a cat here, I have only a bear here, and the question is it dead or alive if one does not watch the process which kills it. But that's another story, and it's better to wrap it up.